What if everything we thought we knew about the universe was just the tip of the iceberg? Picture a world where particles defy logic, appearing in two places at the same time, where the fabric of space itself stretches and warps like a cosmic trampoline, and where the secrets of reality might be hiding inside the inky depths of black holes. This isn't science fiction, it's the breathtaking frontier of quantum physics, a revolution that's turning our understanding of the cosmos upside down. For centuries, we've gazed at the stars with wonder, but today, we're on the verge of unraveling mysteries that were once thought impossible to solve. From the mind-bending phenomenon of quantum entanglement to the elusive nature of dark matter, science is rewriting the rules of existence, one discovery at a time. Think about the last time you looked up at the night sky and felt that familiar hum of curiosity. That same awe has driven humanity's greatest minds to ask the big questions. What is the universe made of? How does it really work? And where do we fit into it all? Now imagine standing at the edge of a quantum leap, a moment in history where the answers to these questions aren't just speculation but tangible, thrilling truths. Scientists are now peering into realms where time behaves strangely, where information can teleport across vast distances, and where the very building blocks of reality might be connected in ways we're only beginning to grasp. It's as if the universe has been whispering its secrets, and we're finally learning how to listen. This journey isn't just for physicists in lab coats, it's for anyone who's ever marveled at the stars or questioned the nature of reality. Over the next few minutes, we'll dive into discoveries that sound like they're pulled from the pages of a fantasy novel, except they're very, very real. We'll explore how quantum entanglement could revolutionize communication, how dark matter's invisible grip shapes galaxies, and why black holes might be the ultimate cosmic puzzles. Each revelation challenges our assumptions, pushing the boundaries of what we thought was possible. So buckle up, because by the end of this, you'll see the universe in a whole new light, and you might just wonder how we ever settled for the ordinary when the extraordinary was waiting to be discovered. The story of quantum mechanics begins not with a bang, but with a flicker of light, specifically the glow of a hot oven. In the year 1900, German physicist Max Planck was wrestling with a puzzle that had stumped scientists for decades. No matter how carefully they measured, the energy radiating from heated objects refused to match the predictions of classical physics. The math simply didn't add up until Planck made a radical suggestion. What if energy wasn't a smooth, continuous flow like water from a faucet, but instead came in tiny, indivisible chunks? He called these packets quanta. And with that single idea, the foundation of classical physics began to crack. Planck himself didn't fully grasp the implications of his discovery. It took a young patent clerk named Albert Einstein to realize just how revolutionary this idea truly was. 5 years later, Einstein applied Planck's quantum theory to another baffling phenomenon: the photoelectric effect, where light striking metal could knock electrons loose. Classical physics insisted light was a wave, but Einstein proposed something astonishing. Light also behaved as a particle, carrying energy in those same discrete packets Planck had described. This dual nature of light, both wave and particle, was the first clear sign that the microscopic world played by entirely different rules than the universe we see around us. Then came the 20s, a golden age of quantum upheaval. Werner Heisenberg introduced his uncertainty principle, showing we can never perfectly measure both a particle's position and its momentum at the same time. Schrödinger countered with his famous wave equation, painting electrons not as tiny balls but as smeared-out clouds of probability. And Niels Bohr's Copenhagen interpretation declared that particles don't even have definite properties until we observe them, a notion so strange that even Einstein famously objected, insisting God does not play dice. These weren't just abstract ideas. They emerged from real, tangible experiments that defied common sense. The double-slit experiment revealed electrons could act as both particles and waves, as if a single electron could pass through two openings simultaneously. The Stern-Gerlach experiment showed particles mysteriously aligning with magnetic fields in quantized, step-like ways. Each discovery peeled back another layer of reality, revealing a subatomic world far wilder than anyone had imagined. What's astonishing isn't just how quickly these breakthroughs came, it's how they forced scientists to abandon intuition entirely. The quantum realm doesn't behave like the predictable clockwork universe Newton described. Instead, it's a place of probability where particles tunnel through barriers like ghosts, where entangled twins instantly mirror each other across galaxies, and where the very act of looking changes what's there. This wasn't just a new chapter in physics, it was a rewrite of the entire book, one that still keeps us questioning today. Einstein may have been a titan of physics, but even he had his limits, and quantum entanglement pushed him right to the edge. In 1935, he co-authored a paper with colleagues Podolsky and Rosen, aiming to expose what he saw as a glaring flaw in quantum theory. They described a thought experiment where two particles, once linked, could be separated by vast distances, yet measuring one would instantly determine the state of the other, as if they were still touching. To Einstein, this violated the very bedrock of relativity, which insisted nothing could travel faster than light. He dismissed it as spooky action at a distance, a sign that quantum mechanics must be incomplete. But here's the twist. Einstein's attempt to debunk entanglement ended up highlighting one of quantum theory's most astonishing truths. Decades later, physicist John Bell devised a way to test whether these spooky connections were real. His equations set the stage for experiments that would settle the debate once and for all. In the 1980s, Alain Aspect and his team fired pairs of entangled photons in opposite directions, measuring their properties at separate detectors. The results were unmistakable. The particles correlated in ways that defied classical explanation, as if they were communicating faster than the speed of light. This wasn't just a laboratory curiosity. Entanglement hints at a universe far more interconnected than we ever imagined. Picture two coins flipped on opposite sides of the galaxy, always landing heads and tails in perfect sync, no matter the distance. That's the eerie reality of entangled particles, and it gets stranger. This connection isn't about transmitting information in the traditional sense. You can't use entanglement to send a message faster than light, at least not with our current understanding. Instead, it's as if the particles share a hidden layer of reality, a deeper framework where distance simply doesn't matter. The implications ripple across physics and beyond. Quantum encryption already leverages entanglement to create theoretically unhackable communication. Any eavesdropping would disturb the delicate link, alerting the users instantly. Some theorists even speculate that spacetime itself might emerge from a vast network of entangled quantum bits, weaving the cosmos together like threads in a cosmic tapestry. And then there's the tantalizing possibility of quantum teleportation, where information not matter jumps between entangled particles, opening doors to technologies we've only dreamed of. Einstein's skepticism forced science to confront the bizarre heart of quantum mechanics, and in doing so, he accidentally handed us a key to the universe's deepest mysteries. What once seemed like spooky action now looks like a fundamental feature of reality, whispering that the cosmos is far stranger and far more connected than we ever dared to believe. If you ever needed proof that the quantum world operates on a different set of rules, the double-slit experiment delivers it in spectacular fashion. At first glance, it seems simple enough. A beam of particles, like electrons or photons, is fired toward a barrier with two narrow slits. On the other side, a detector screen records where these particles land. Common sense suggests they should pass through one slit or the other, leaving two distinct bands on the screen. But that's not what happens. Instead, the screen lights up with a series of alternating light and dark stripes, an interference pattern, the unmistakable signature of a wave. Somehow, particles are behaving as though they're rippling through both slits at once, overlapping and canceling each other out like waves in a pond. Here's where things get truly mind-bending. When scientists decided to observe which slit each particle actually travels through, the interference pattern vanished. The particles suddenly behaved like tiny bullets again, hitting the screen in two neat clusters. It's as if the mere act of looking forced them to abandon their wave like nature and choose a single path. This isn't just a quirk of the setup, it's a fundamental feature of reality at the smallest scales. Particles exist in a haze of possibilities until measured, and the moment we try to pin them down, they snap into a defined state. The implications ripple far beyond the laboratory. For one, it suggests that the universe doesn't have a single, fixed reality independent of observation. Instead, what we perceive is shaped by our interactions with it, a notion that blurs the line between the observer and the observed. Some interpretations, like the Copenhagen school, argue that particles don't have definite properties until measured. Others, like the many worlds theory, propose that every possible outcome actually happens, splitting the universe into countless branches where each version of events plays out. Then there's the elephant in the room, consciousness. Does the act of measurement require a human observer, or is any interaction with the environment enough to collapse these probabilities? Experiments with increasingly sophisticated detectors have shown that even machines can trigger this shift, but the debate rages on. Could consciousness play some deeper role in shaping reality, or is this just a quirk of quantum math? What makes the double-slit experiment so extraordinary isn't just the weirdness it reveals, it's how stubbornly that weirdness resists easy explanation. Centuries after Newton, we're still grappling with the fact that the building blocks of reality don't follow the rules we grew up with. Particles aren't just tiny billiard balls, they're ephemeral, shape-shifting entities that defy location and logic. And every time we think we've got them figured out, they slip through our fingers like smoke, leaving us with more questions than answers. Werner Heisenberg's uncertainty principle didn't just challenge physics, it shattered the very idea that we could ever know everything with perfect precision. Imagine trying to measure the exact position and speed of a hummingbird in flight. The moment you pinpoint its location, its movement becomes a blur, and when you focus on its speed, its exact position slips away. At the quantum level, this isn't a limitation of our tools, it's a fundamental property of reality. Heisenberg revealed that the more precisely we measure a particle's position, the less we can know about its momentum, and vice versa. This isn't about human error, it's woven into the fabric of the universe itself. The implications ripple far beyond the lab. Take the humble electron orbiting an atom. Classical physics pictured it like a planet circling the sun with a clear path and velocity, but Heisenberg showed that's impossible. The electron doesn't follow a neat orbit. Instead, it exists as a cloud of probabilities, a haze of possible positions and speeds. The act of measuring one property inevitably disturbs the other, as if reality resists being pinned down. This blurriness isn't a flaw, it's what allows atoms to exist at all. Without uncertainty, electrons would spiral into the nucleus, collapsing matter as we know it. What makes this principle so revolutionary is how it redefines the limits of knowledge. For centuries, science operated on the assumption that with better instruments, we could measure anything perfectly. Heisenberg proved some doors will always stay closed, not because we aren't clever enough, but because the universe refuses to reveal certain pairs of secrets simultaneously. It's as if nature has built-in privacy settings, keeping some aspects of reality forever just out of focus. This isn't just philosophical, it shapes modern technology. Quantum computers leverage uncertainty, using particles that exist in multiple states at once to perform calculations impossible for classical machines. Even the lasers in your DVD player rely on the delicate balance between a photon's position and momentum, a dance dictated by Heisenberg's rule. And then there's the cosmic scale. The uncertainty principle may explain why empty space isn't truly empty, but a seething foam of virtual particles popping in and out of existence, borrowing energy from the void before vanishing again. Heisenberg didn't just give us a new equation, he handed us a lens to see the universe as it truly is. Not a clockwork mechanism, but a living, breathing puzzle where certainty and ambiguity exist in an eternal embrace. The more we try to grasp one aspect of reality, the more another slips through our fingers, reminding us that the cosmos thrives on mystery as much as it does on order. Schrödinger never meant for his cat to become famous, at least not in the way it did. The year was 1935, and the physicist was wrestling with the bizarre implications of quantum superposition, the idea that particles could exist in multiple states at once until measured. To highlight how absurd this seemed when applied to everyday objects, he devised a gruesome thought experiment. Imagine a cat sealed in a box with a radioactive atom, a Geiger counter, and a vial of poison. If the atom decays, the counter triggers the release of the poison, killing the cat. But according to quantum rules, until someone opens the box, the atom exists in a superposition, both decayed and not decayed, meaning the cat must be simultaneously alive and dead. Schrödinger's point wasn't that cats could defy biology, but that quantum mechanics, when stretched to macroscopic scales, led to paradoxes that clashed with our experience of reality. Yet here's the twist: superposition isn't just a theoretical quirk. In labs today, scientists routinely create tiny cats, not feline, but particles and even molecules suspended between states. Take quantum computers, where bits called qubits exploit superposition to perform calculations at unimaginable speeds. Unlike classical bits stuck as zeros or ones, a qubit can be both at once, allowing it to explore multiple solutions simultaneously. It's as if you could try every possible key in a lock at the same instant, finding the right one in a fraction of the time. The real magic happens when superposition teams up with entanglement. Together, they enable quantum machines to solve problems that would take conventional computers millennia, like simulating complex chemical reactions to design life-saving drugs or cracking encryption protocols that guard global data. Companies like Google and IBM have already built rudimentary quantum processors, marking the first steps toward this revolution. But there's a catch: superposition is fragile. The slightest disturbance, a stray photon, a vibration, can collapse these delicate states, a phenomenon called decoherence. That's why quantum computers operate in frigid, isolated chambers, shielding their qubits from the noisy world outside. Beyond technology, superposition forces us to confront profound questions about existence. If particles only choose a state when observed, does reality truly exist independently of measurement? Some interpretations, like the many worlds theory, suggest every possible outcome branches into a new universe, meaning there's a world where the cat lives and another where it dies, both equally real. Others propose that consciousness itself plays a role in shaping reality, though this remains hotly debated. What Schrödinger intended as a critique has become a gateway to understanding quantum theory's radical heart. Superposition isn't just a laboratory trick, it's a window into a universe far more fluid and interconnected than our senses suggest. From the eerie silence of a quantum processor to the unresolved mysteries of observation, one thing is clear: the line between the possible and the impossible is thinner and far stranger than we ever imagined. If walls could talk, they'd tell you about the quantum particles that slip right through them. Picture this: a ball rolling toward a hill. In the classical world, if it doesn't have enough energy to reach the top, it rolls back down. But in the quantum realm, particles play by different rules. Even when faced with a barrier they seemingly can't overcome, there's a chance they'll simply appear on the other side, as if they've teleported. This isn't magic, it's quantum tunneling, one of the most bizarre yet consequential phenomena in physics. The secret lies in the probabilistic nature of quantum mechanics. Particles like electrons don't have definite positions. They're described by wave functions, clouds of probability that represent where they might be. These wave functions don't abruptly stop at barriers, they taper off, extending slightly beyond. That means there's always a tiny, non-zero chance the particle will tunnel through, materializing where it logically shouldn't be. It's like tossing a coin into a sealed jar and finding it outside moments later with no cracks in the glass. This isn't just a theoretical curiosity. Quantum tunneling is the reason the sun shines. Inside stars, hydrogen nuclei repel each other due to their positive charges, creating an energy barrier that should prevent fusion. But thanks to tunneling, protons occasionally sneak through this barrier, allowing them to collide and fuse into helium, releasing the energy that lights up the cosmos. Without tunneling, stars including our sun would be dark, cold, and lifeless. Closer to home, tunneling powers the technology in your pocket. The transistors in modern computer chips have shrunk so small that electrons now tunnel through insulating layers, a challenge engineers must carefully manage. But tunneling isn't just a nuisance, it's a tool. Scanning tunneling microscopes use this effect to image individual atoms, dragging a needle so close to a surface that electrons tunnel across the gap, creating a map of the atomic landscape. It's how we've visualized the building blocks of matter with breathtaking precision. The future holds even wilder possibilities. Researchers are exploring tunneling to create ultra-fast, energy-efficient electronics that leap past the limits of silicon. Imagine computers where data doesn't travel, it teleports across barriers, slashing power consumption. There's even speculation about harnessing tunneling for quantum batteries, devices that could charge instantly by leveraging these probabilistic jumps. Yet tunneling also reminds us how much we still don't understand. Why does the universe permit such loopholes? Is there a deeper principle at work, or is this simply the way reality stitches itself together? Every time a particle tunnels, it's as if the cosmos winks at us, hinting that the rules we take for granted are far more flexible and far more mysterious than we ever imagined. What if every choice you've ever made, and every choice you didn't, exist somewhere out there in an infinite web of realities? That's the spine-tingling promise of the many worlds interpretation, a bold answer to one of quantum mechanics' biggest headaches, the measurement problem. When Hugh Everett first proposed his theory in 1957, it seemed like science fiction. While the Copenhagen interpretation insisted quantum probabilities collapse into a single outcome when observed, Everett dared to suggest something far more radical. There is no collapse. Instead, every possible outcome plays out just in a branching series of parallel universes. Think of it like a cosmic choose-your-own-adventure book where every decision splinters the story. Flip a quantum coin, and in one universe it lands heads, in another it's tails. But here's the kicker: those branches aren't just about coin flips. They multiply with every particle interaction, every atomic event, creating an ever-expanding multiverse where every conceivable version of history unfolds simultaneously. Missed the bus this morning? Somewhere you caught it. Wondered what life would be like if you'd taken that job offer? Another version of you is living it right now. This isn't just philosophy. It's a mathematically rigorous framework that dodges the thorny issue of wave-function collapse. In the many worlds view, reality is a single, ever-evolving quantum state, and what we perceive as random outcomes are just our limited perspective on a tapestry of diverging timelines. No observers are privileged, no measurement is special. The universe simply keeps all possibilities in play, forever splitting but never truly separating. Critics argue the theory is untestable. How can we prove the existence of universes we'll never see? Yet supporters counter that it's the most elegant solution to quantum weirdness, free from the arbitrary measurement triggers of other interpretations. And tantalizingly, some versions of string theory now suggest these parallel realities might not be entirely disconnected. Higher dimensions or quantum entanglement could leave faint fingerprints, cosmic echoes of our alternate selves. The implications ripple far beyond physics. If many worlds is correct, identity becomes a kaleidoscope. You aren't a single thread but a spectrum of variations, each equally real. Time isn't a line but a frothing ocean of possibilities. Even death loses its finality. In some branch you'll always persist. It's a vision both exhilarating and unsettling, reminding us that reality might be vaster, stranger, and more interconnected than our minds can fathom. Everett's theory began as a graduate student's daring thought experiment. Today, it challenges us to reconsider not just the nature of the universe, but our place within it, not as singular observers, but as participants in an infinite dance of possibilities. Whether the many worlds interpretation is ultimately proven or not, it has already reshaped our deepest questions about existence, leaving us to wonder, in the grand symphony of the multiverse, how many versions of this conversation are happening right now? Imagine a universe where most of the matter isn't just hidden, it's fundamentally invisible, not cloaked in shadows, not tucked behind cosmic dust, but utterly undetectable by light, radio waves, or any form of electromagnetic radiation we've ever devised. This isn't hypothetical. Right now, as you read these words, streams of dark matter are passing through your body, through the floor beneath you, through the entire Earth as if it weren't even there. Yet despite making up 27% of the cosmos, 5 times more than all the atoms in stars, planets, and galaxies combined, we've never directly seen it, touched it, or fully understood it. The story of dark matter begins not with a discovery, but with a discrepancy. In the 1930s, Swiss astronomer Fritz Zwicky was studying the Coma cluster, a group of galaxies bound together by gravity. When he calculated the mass of the visible stars and gas, then compared it to the speed at which the galaxies were orbiting each other, the numbers didn't add up. The cluster was moving far too fast. It should have flung itself apart long ago unless some unseen mass was holding it together. Zwicky called this missing ingredient dunkel materie, or dark matter, but his peers dismissed it as a curiosity. Decades later, Vera Rubin's meticulous observations of spinning galaxies revealed the same puzzle. Stars at the edges of galaxies were orbiting just as fast as those near the center, defying Newton's laws. The only explanation, an invisible halo of matter exerting gravitational pull without emitting light. So what is this elusive substance? The leading candidates are WIMP, weakly interacting massive particles, hypothetical entities that barely interact with normal matter except through gravity. Think of them as cosmic ghosts drifting through walls, stars, even you, without a trace. Then there's the action, an ultra-lightweight particle born from theories attempting to solve quantum puzzles. Some scientists even speculate dark matter could be primordial black holes, remnants of the Big Bang lurking unseen in the voids between stars, but the plot thickens. Recent observations of galaxies with little to no dark matter have thrown a wrench into the mix. If dark matter is supposed to be everywhere, why do these outliers exist? Could our understanding of gravity itself need revision, as theories like modified Newtonian dynamics suggest? Or is dark matter more complex, with multiple types interacting in ways we haven't yet imagined? Here's where the cosmic scaffolding comes in. Supercomputer simulations show that without dark matter's gravitational pull, the universe would look radically different. After the Big Bang, normal matter was too hot and energetic to clump together efficiently. Dark matter, unaffected by radiation, acted as a gravitational glue, forming vast webs that drew atoms into its embrace. Galaxies grew at the intersections of these invisible filaments, like dew collecting on a spider's web. Even now, dark matter's hidden architecture dictates the large-scale structure of the cosmos, guiding the motion of galaxies in ways we're only beginning to map. The hunt for direct detection is fiercer than ever. Labs buried deep underground, shielded from cosmic noise, wait for the infinitesimal shudder of a dark matter particle colliding with an atom. Space telescopes trace the distortions of light caused by dark matter's gravity bending spacetime itself. Particle colliders aim to manufacture dark matter in bursts of energy, however fleeting. Every null result narrows the possibilities, inching us closer to an answer. What keeps scientists awake at night isn't just the mystery, it's the stakes. Dark matter isn't some peripheral oddity. It's the hidden choreographer of the cosmic dance, the unseen hand that shaped everything we see. Unraveling its nature could rewrite the story of the universe from its birth to its ultimate fate. And perhaps the most humbling thought of all, we're only seeing half the stage. The rest remains shrouded in darkness, waiting for the moment we finally shed light on the invisible threads holding reality together. If dark matter is the universe's invisible scaffolding, then dark energy is its mysterious architect, reshaping the cosmos in ways that defy gravity itself. Picture the universe not as a static stage, but as an expanding balloon, with galaxies drifting farther apart as the fabric of space stretches. Now imagine someone suddenly blowing harder into that balloon, accelerating its growth. That's the enigma of dark energy, a force so perplexing that it makes up a staggering 68% of the universe's total energy, yet we know almost nothing about it. The story begins in the late 1990s, when two teams of astronomers set out to measure the universe's expansion rate by studying distant supernovae. They expected to find that gravity, pulling matter together, was gradually slowing the cosmic expansion left over from the Big Bang. Instead, they discovered the opposite. The universe wasn't just expanding, it was speeding up, as if some invisible repulsive force were pushing galaxies apart at an ever-increasing rate. The shock was so profound that it earned the researchers a Nobel Prize, and physicists scrambled to explain what could possibly be driving this acceleration. Enter dark energy, the placeholder name for whatever's causing this cosmic antigravity. The leading candidate, Einstein's cosmological constant, a term he originally inserted into his equations to keep the universe static, later calling it his greatest blunder when Edwin Hubble proved the cosmos was expanding. Now it's back in play, representing the energy of empty space itself. Quantum theory suggests that a vacuum isn't truly empty but seethes with virtual particles flickering in and out of existence. These fleeting fluctuations could generate a repulsive force, stretching spacetime from within. The problem: calculations predict a vacuum energy trillions of times stronger than what we observe. This discrepancy, known as the cosmological constant problem, remains one of physics' greatest unsolved puzzles. But dark energy's implications are even more staggering. If this acceleration continues unchecked, the universe could face a big freeze, a slow, cold death where galaxies vanish over the horizon of visibility, stars burn out, and space becomes an infinite, empty void. Distant civilizations billions of years from now might look up at a black, starless sky, with no evidence of the universe's rich history beyond their own isolated galaxy. Yet there are other, darker possibilities. What if dark energy isn't constant but evolves over time? Some theories suggest it could grow stronger, eventually tearing apart galaxies, stars, and even atoms in a catastrophic Big Rip. Alternatively, it might fade away, allowing gravity to reverse the expansion and collapse the universe in a big crunch. The truth is, we're still grasping at shadows. Current telescopes, like the Dark Energy Survey and the upcoming Euclid mission, are mapping billions of galaxies to trace how dark energy's influence has changed over cosmic history. The most humbling realization: we're witnessing just a fleeting moment in the universe's story. Dark energy was negligible in the early cosmos, and for billions of years, matter's gravity dominated. But around 5 billion years ago, as the universe grew more spacious, dark energy's push overtook gravity's pull. Now it's steering the fate of everything. And just as Copernicus showed Earth wasn't the center of the solar system, dark energy reminds us that our existence is a tiny, fragile spark in a vast, accelerating cosmos, one that might one day leave no trace we were ever here at all. Black holes aren't just cosmic vacuum cleaners, they're the ultimate laboratories for testing the limits of physics. At their edges, gravity grows so intense that not even light can escape, and the familiar rules of space and time twist into something unrecognizable. But here's where it gets even stranger. Deep inside a black hole's grip, two of science's most successful theories, Einstein's general relativity and quantum mechanics, clash in an epic battle, leaving physicists with a paradox that could rewrite our understanding of reality itself. Take Hawking radiation, one of the most startling discoveries in modern cosmology. In the 1970s, Stephen Hawking made a revolutionary prediction: black holes aren't completely black. Thanks to quantum fluctuations near the event horizon, the point of no return pairs of particles can pop into existence. Normally, these particles annihilate each other instantly, but if one falls into the black hole while the other escapes, the whole loses a tiny bit of mass. Over eons, this slow leak means even the mightiest black holes could evaporate entirely. It's a breathtaking idea. Black holes, those symbols of eternal darkness, might actually fade away like morning mist. But this revelation came with a catch: the infamous information paradox. According to quantum mechanics, information about particles can never be truly destroyed. Yet if a black hole evaporates, what happens to all the matter and energy it swallowed? Does that information vanish into oblivion, or is it somehow encoded in the radiation? For decades, physicists wrestled with this puzzle, with Hawking initially betting that information was lost forever. Then came the holographic principle, a radical idea suggesting that all the data about what falls into a black hole might be preserved on its surface like a cosmic fingerprint. Imagine a three-dimensional object being perfectly described by a two-dimensional shadow. That's the essence of this theory, where the universe might store information in ways we're only beginning to grasp. The stakes couldn't be higher. If black holes preserve information, they might hold the key to unifying gravity and quantum mechanics, the holy grail of theoretical physics. Some researchers propose that inside a black hole, space and time dissolve into a seething quantum foam, where the fabric of reality itself is rewoven. Others suggest black holes could be gateways to other universes, or even quantum computers of unimaginable power. The truth might lie in string theories, extra dimensions, or loop quantum gravities woven spacetime, but one thing's certain: black holes are forcing us to confront the deepest questions about existence. What makes this quest so urgent isn't just theoretical curiosity. It's the chance to glimpse the universe's underlying code. Every time a black hole flickers with Hawking radiation or collides in a gravitational wave event, it's as if the cosmos is sending us encrypted messages about how it truly works. And with telescopes now peering into the hearts of galaxies and labs simulating black hole conditions, we're closer than ever to cracking the code. The answers won't just rewrite textbooks. They could reveal whether reality is a hologram, a simulation, or something far stranger than we've ever dared to dream. What if the universe we perceive with its galaxies, stars, and even our own bodies is nothing more than an illusion, a cosmic mirage projected from a hidden two-dimensional surface? This is the mind-bending premise of the holographic principle, a theory so radical it challenges our most basic assumptions about reality. The idea first emerged from the study of black holes, where physicists discovered something astonishing. The maximum amount of information a black hole can contain isn't proportional to its volume, as you'd expect, but to the area of its event horizon. It's as if all the data describing everything inside a black hole could be encoded on its surface, like a celestial DVD storing a three-dimensional movie on a flat disk. This discovery sent shockwaves through theoretical physics. If black holes obey this rule, could the entire universe? The holographic principle suggests that our 3D reality, every atom, every force, even your thoughts, might be a projection from a vast, distant 2D boundary we'll never see. Picture a movie screen where the images appear to have depth, but the information creating that illusion exists only in the flat pixels of the screen itself. In this view, spacetime isn't fundamental. It's an emergent phenomenon woven from something deeper and far stranger. The implications ripple across science. For one, the holographic principle could finally reconcile quantum mechanics and general relativity, two theories that have stubbornly resisted unification. Quantum physics thrives in flat, simple spaces, while Einstein's gravity sculpts the dynamic curves of spacetime. But if spacetime is a hologram, gravity might just be a shadow of quantum processes playing out on a hidden 2D surface. This could explain why gravity is so weak compared to other forces. It's not a fundamental force at all, but a side effect of deeper quantum interactions. Experiments are already testing this wild idea. Fermilab's holometer searches for tiny pixelation in spacetime, hunting for evidence that reality has a finite resolution like a digital image. Meanwhile, studies of the cosmic microwave background, the afterglow of the Big Bang, look for anomalies that might hint at a universe encoded on a distant horizon. So far, the results are inconclusive, but the very possibility has reshaped how we think about existence. Critics argue the holographic principle is untestable philosophy, but supporters counter that it's the most elegant solution to some of physics' biggest paradoxes. After all, if the universe is a hologram, it would explain why information can't be destroyed even in black holes, because the real data is safely stored elsewhere, untouched by the chaos of our 3D world. What makes this theory so compelling isn't just its audacity. but the way it turns our intuition inside out. We're so accustomed to thinking of space as the stage and matter as the actors, but the holographic principle flips the script. The stage itself might be an illusion, a shimmering projection of something far simpler and more profound. Whether it's ultimately proven or not, this idea forces us to confront the unnerving possibility that reality isn't just stranger than we imagine. It might be stranger than we can imagine. Quantum computing doesn't just push the boundaries of technology, it shatters them entirely. Unlike classical computers, which rely on bits that can only be 0 or 1, quantum computers harness qubits, particles that exist in a superposition of both states simultaneously. Picture a coin spinning in midair until it lands. It's neither heads nor tails, but a fluid blend of possibilities. Now imagine millions of these spinning coins working in concert, exploring countless solutions at once. That's the power of superposition, and when combined with entanglement, the eerie link that binds qubits across space, it unlocks computational abilities that defy classical logic. Take cryptography, the backbone of digital security. Today's encryption relies on mathematical problems so complex that even supercomputers would take millennia to crack them. But a quantum machine could factor enormous numbers almost instantly, rendering current security protocols obsolete. Governments and corporations are already racing to develop quantum-resistant encryption, knowing the moment these machines mature, the digital world will need a radical overhaul. Yet quantum computing isn't just about breaking codes, it's about creating unbreakable ones. Quantum key distribution uses entangled particles to transmit information so securely that any eavesdropping attempt would immediately disrupt the connection, alerting both parties. Medicine stands on the brink of its own revolution. Simulating molecular interactions is a nightmare for classical computers. Even a simple protein folding can require unfathomable calculations. Quantum computers, however, could model these processes atom by atom, accelerating drug discovery by decades. Imagine designing a cure for Alzheimer's by precisely mapping how compounds interact with brain proteins, or crafting personalized cancer treatments tailored to a patient's unique DNA. The implications stretch beyond biology. Quantum simulations could unlock room temperature superconductors, revolutionizing energy grids, or optimize complex systems like global supply chains with unprecedented efficiency. Then there's space exploration. Navigating the cosmos demands solving equations with countless variables, trajectories, gravitational pulls, fuel efficiency, all while accounting for the chaos of deep space. Quantum algorithms could plot optimal paths to Mars or beyond, minimizing risks and maximizing discovery. They might even help decode the universe's grandest mysteries, like dark matter's structure or the origins of cosmic inflation, by processing vast datasets from telescopes in ways classical systems never could. But here's the catch: quantum computers are temperamental. Their delicate quantum states collapse at the slightest disturbance, a phenomenon called decoherence. Leading labs combat this by cooling qubits to near absolute zero or isolating them in ultra-stable vacuums. Companies like IBM and Google have built machines with hundreds of qubits, but error rates remain high. The dream of fault-tolerant quantum computing, where errors are corrected faster than they occur, is still on the horizon. What makes this field so electrifying isn't just the technology, it's the paradigm shift. We're not just building faster computers, we're redefining problem-solving itself. From unbreakable networks to bespoke medicines, from interstellar travel to unlocking the fabric of reality, quantum computing isn't the next step in tech, it's a leap into the unknown. And the most thrilling part, we're just beginning to glimpse what's possible. For centuries, biology and physics seemed to occupy entirely separate worlds, one studying the vibrancy of life, the other the cold mechanics of particles. But what if the boundary between them is far blurrier than we ever imagined? Enter quantum biology, a field that reveals nature's hidden quantum handiwork in everything from the flutter of a leaf to the navigation of a migrating bird. At first glance, life seems too warm, too wet, too chaotic for delicate quantum effects to survive. Yet somehow, evolution has hacked the subatomic realm, weaving quantum phenomena into the very fabric of life's most essential processes. Take photosynthesis, the elegant dance that turns sunlight into energy. Classical biology long assumed this was a straightforward game of molecular hot potato photons absorbed by chlorophyll, pass their energy randomly through a network of molecules until it reaches the reaction center. But experiments revealed something astonishing. Energy doesn't bounce aimlessly. Instead, it explores multiple pathways simultaneously, leveraging quantum coherence to find the most efficient route with near-perfect precision. It's as if plants perform instantaneous quantum calculations to optimize sunlight harvesting, a trick our most advanced solar panels still can't replicate. Then there's the mystery of avian navigation. Every year, birds like the European robin embark on migrations spanning thousands of miles, guided by Earth's faint magnetic field. The secret might lie in a quantum quirk inside their eyes. Cryptochrome, a light-sensitive protein, could host entangled electron pairs whose spin states shift in response to magnetic fields, creating a biological compass sensitive enough to detect changes weaker than a millionth of Earth's magnetism. If confirmed, this would mean birds literally see the planet's magnetic lines as visual patterns, a quantum sense humans can scarcely fathom. Even our own DNA isn't immune to quantum weirdness. The helix's double-strand structure may rely on proton tunneling, where hydrogen atoms teleport across positions to maintain genetic stability. Enzymes, those molecular workhorses speeding up life's chemical reactions, might exploit quantum tunneling to slash reaction times from millennia to milliseconds. Some researchers speculate that quantum vibrations in microtubules, tiny structures inside neurons, could play a role in consciousness itself, though this remains hotly debated. The implications are staggering. If quantum effects are ubiquitous in biology, life might not be an accident of classical chemistry, but an ingenious user of subatomic shortcuts. This could revolutionize medicine. Imagine drugs designed with quantum tunneling in mind, or bioengineered photosynthesis to tackle climate change. It also forces us to rethink the boundaries of life. Could quantum coherence explain why living systems seem so exquisitely tuned, or even hint at deeper connections between mind and matter? Critics argue these phenomena are too fragile to persist in noisy biological environments, but nature's mastery of quantum mechanics suggests otherwise. Evolution, it seems, has spent billions of years perfecting tricks that physicists are only now uncovering. From the quantum whispers in a leaf to the entangled compass in a bird's eye, life isn't just playing by quantum rules, it's rewriting them. And as we peer deeper into this hidden layer of biology, we might discover that the line between the living and the quantum isn't just blurred, it might not exist at all. The standard model is like a cosmic recipe book, one that lists every known ingredient in the universe and the rules for how they interact. At its heart are 12 fundamental particles, 6 quarks, which combine to form protons and neutrons, and 6 leptons, including the familiar electron. These particles are the building blocks of everything we see, from the screen in front of you to the farthest stars. But matter isn't complete without the forces that glue it together. Enter the force carriers, photons for electromagnetism, gluons for the strong nuclear force, and W and Z bosons for the weak force. Then there's the Higgs boson, the last piece of the puzzle, discovered in 2012 after a decades-long hunt. This elusive particle is what gives all others their mass, like an invisible molasses slowing them down as they move through the Higgs field. Yet for all its elegance, the Standard Model is frustratingly incomplete. It doesn't account for gravity, general relativity's domain, or explain why the universe is filled with dark matter, an invisible substance that outweighs normal matter 5 to 1. There's also the mystery of antimatter. According to the model, the Big Bang should have created equal amounts of matter and antimatter, which would have annihilated each other, leaving behind a lifeless cosmos. But here we are in a universe dominated by matter with no clear explanation for the imbalance. The gaps don't stop there. Neutrinos, those ghostly particles that stream through you by the trillions every second, have mass something the original Standard Model didn't predict. And then there's dark energy, the mysterious force accelerating the universe's expansion, which doesn't fit anywhere in the framework. These omissions hint at something bigger lurking beyond our current understanding, like a shadow just outside the edge of a flashlight's beam. Scientists aren't sitting idle. Particle colliders like the Large Hadron Collider are smashing protons together at near light speeds, searching for anomalies that could crack the model wide open. Theories like supersymmetry propose a hidden family of particles that could explain dark matter, while string theory weaves gravity into the quantum realm using tiny, vibrating strands of energy. Some researchers even speculate about extra dimensions, curled up so small we'd never notice them unless a high-energy collision ripped them open. What makes the Standard Model so remarkable isn't just what it explains, but what it leaves unanswered. Every gap is a doorway to a deeper layer of reality, a reminder that the universe still holds secrets waiting to be uncovered. And as we peer deeper into the quantum world, we might just find that the rules we've written are only the first draft of a much grander story. What if the smallest building blocks of reality aren't dots at all, but dancing strands of energy, vibrating in hidden dimensions we can't even see? This is the bold vision of string theory, a framework so ambitious it aims to stitch together all the forces of nature, gravity, electromagnetism, and the nuclear forces into a single, elegant equation. Forget particles as tiny billiard balls. Here, everything from electrons to black holes emerges from microscopic strings, each vibrating at different frequencies like the strings of a cosmic violin. Pluck one string and you get an electron, pluck another and you've created a quark. The universe, in this view, isn't a collection of objects but a symphony of vibrations. The allure of string theory lies in its sheer scope. For decades, physicists have struggled to reconcile Einstein's general relativity, which governs the cosmos on large scales, with quantum mechanics, which rules the subatomic realm. The two theories clash violently at extremes like the center of black holes or the moment of the Big Bang. String theory offers a way out by rewriting particles as strings. It smooths over the mathematical cracks, providing a playground where gravity and quantum forces can coexist harmoniously. But there's a catch-one that's as mind-bending as the theory itself. Strings are so tiny, about 100 billion times smaller than an atomic nucleus, that they'd be impossible to detect with current technology. Worse yet, their equations only work if the universe has extra dimensions, not just the 4 we experience, 3 of space, 1 of time, but 6 or 7 more, curled up into shapes so minuscule we'd never notice them. Picture a garden hose. From afar, it looks like a simple line, but up close, you see it's a cylinder with a hidden circular dimension. String theory suggests space-time might be similarly coiled, with intricate geometries called Calabi-Yau manifolds determining how strings vibrate, and thus what particles and forces emerge. The challenges don't stop there. String theory isn't a single idea but a sprawling landscape of possible solutions, perhaps 10 to the 500 versions of reality, each with different physical laws. This multiverse scenario raises thorny questions. If most universes are inhospitable to life, does that make ours a statistical fluke? And without experimental proof, how do we know string theory isn't just a beautiful mathematical fiction? Critics argue it's more philosophy than physics, while supporters counter that its mathematical consistency is too compelling to ignore. Yet even skeptics admit string theory has reshaped modern physics. It's inspired breakthroughs in black hole thermodynamics, suggesting that the information swallowed by a black hole might live on its surface, a precursor to the holographic principle. It's also fueled advances in pure mathematics, helping solve problems in geometry and topology that once seemed untouchable. And then there's M-theory, a bold extension that unites 5 competing string theories under one umbrella, hinting at an even deeper structure where strings are just one piece of a larger puzzle involving membranes or brains existing in higher dimensional spaces. What keeps physicists hooked is the tantalizing possibility that string theory might finally answer the ultimate question: why this universe? If it's right, the laws of physics, the strength of gravity, the mass of an electron, even the existence of time, could all stem from the way strings vibrate in the hidden folds of reality. For now, it remains a dazzling work in progress, a theory so beautiful and so elusive that it's been called a piece of 21st century physics that fell into the 20th century by accident. Whether it's the final word or just a stepping stone, one thing's certain: the quest to unify reality is far from over, and string theory has already rewritten the map. While string theory dreams of hidden dimensions and vibrating strings, loop quantum gravity takes a radically different approach, one that doesn't ask us to imagine unseen worlds, but to rethink the very fabric of space and time. Picture the universe not as a smooth, continuous expanse, but as a shimmering tapestry woven from countless tiny loops, each smaller than an atom. These aren't physical wires, but fundamental threads of spacetime itself, intersecting and braiding together to create the geometry of reality. It's as if the cosmos is built from an unimaginably fine mesh, where even the vacuum of empty space buzzes with quantum connections. This bold idea emerged as a direct challenge to string theory's extra dimensions, offering an alternative path to unifying gravity with quantum mechanics. Instead of particles, loop quantum gravity focuses on spacetime's structure, suggesting that just as matter comes in discrete packets, quanta, so too does space. The theory's founders, Lee Smolin and Carlo Rovelli, proposed that these loops carry quantized areas and volumes, meaning space can't be divided infinitely. There's a smallest possible piece, a pixel of reality roughly 10 to the minus 35 meters across. Step any smaller and you're not moving through space, you're rearranging the network itself. One of the theory's most startling predictions is that time, as we experience it, might be an illusion. At the fundamental level, there's no smooth flow of seconds, but a sequence of discrete quantum jumps like frames in a cosmic film reel. This could reshape how we understand the Big Bang. Rather than a singularity of infinite density, loop quantum gravity suggests a bounce, where a previous universe collapsed before rebounding into ours. It's a vision that replaces the terrifying nothingness of a singularity with a transformational moment, a cosmic pivot where gravity's quantum nature prevents total collapse. But how does this abstract web of loops translate to the world we see? The theory predicts that when particles like electrons move, they're not gliding through passive space. They're tracing paths along this dynamic lattice, their properties defined by how they interact with its knots and twists. Even black holes get a makeover. Their cores might not be infinitely dense points, but extreme distortions of the loop network, where space's weave becomes so tangled it twists into new geometries. Some models suggest black holes could transform into white holes, spewing out matter they once consumed, a dramatic twist on cosmic recycling. Critics argue that loop quantum gravity struggles to explain how the smooth spacetime of general relativity emerges from its choppy quantum foundation. Yet supporters point to recent advances showing how large numbers of loops can statistically blend into the continuous space we observe, much like a digital image. Pixels vanish into a seamless picture when viewed from afar. The theory also boasts concrete predictions, like subtle quantum fluctuations in light from distant gamma-ray bursts, clues we might detect as telescopes grow more precise. What makes this framework so compelling isn't just its mathematics, but its philosophical daring. It demotes space and time from their hallowed status as the universe's stage, recasting them as actors in the quantum play, born from deeper relationships between loops. Whether it ultimately triumphs or not, loop quantum gravity has already shattered an old dogma that reality's fabric must be smooth and infinite. Instead, it whispers a tantalizing possibility that the cosmos might be stitched together from something far stranger, a quantum tapestry where every thread hums with the song of creation itself. The universe began not with a whisper but with a roar, a fireball of unimaginable energy we call the Big Bang. In those first fleeting moments, everything we know, every star, every planet, even the fabric of space itself, was compressed into a space smaller than a single atom. But here's where the story takes a quantum twist. Within that seething cosmic soup, tiny fluctuations flickered into existence, random ripples in the newborn universe's density. These weren't just minor blips, they were the seeds of everything to come, the cosmic blueprints for galaxies, clusters, and the vast web of matter we see today. How do we know this? The answer lies in the oldest light in the cosmos, the cosmic microwave background, or CMB. This faint glow, discovered by accident in 1965, is the afterimage of the Big Bang, cooled over 13.8 billion years into microwave radiation that permeates all of space. When scientists mapped this radiation with satellites like COBE and Planck, they found something extraordinary: tiny temperature variations, patches where the early universe was ever so slightly denser or hotter than average. These imperfections, no larger than 1 part in 100,000, match the predictions of quantum mechanics perfectly. Think of it like a pot of boiling water. At the quantum level, empty space isn't truly empty. It's a frothing sea of virtual particles popping in and out of existence. In the infant universe, gravity amplified these fleeting fluctuations, stretching them across the expanding cosmos. Where matter was slightly denser, gravity pulled in more gas, eventually sculpting galaxies. Where it was thinner, vast cosmic voids formed. The CMB is our snapshot of this process, frozen in time just 380,000 years after the Big Bang, when the universe cooled enough for light to travel freely. But the mystery deepens when we ask why these fluctuations existed at all. Quantum theory suggests they were inevitable, a side effect of the universe's turbulent birth. Yet their precise pattern holds clues to physics beyond our current understanding. Some variations in the CMB hint at primordial gravitational waves, ripples in spacetime from the universe's exponential expansion during inflation, a period when space itself ballooned faster than light. Others might reveal hidden dimensions or exotic particles that vanished long ago. What's astonishing isn't just that we can see these fingerprints of creation, it's how perfectly they align with quantum predictions. The galaxies we observe today, the clusters they form, even the empty voids between them, all trace back to those microscopic quantum jitters in the first trillionth of a second. It's as if the universe played a game of cosmic connect the dots, with quantum mechanics holding the pencil, Yet for all we've uncovered, the CMB still guards secrets. Why is the universe so remarkably uniform on large scales? What caused inflation to start or stop? And could there be other, older universes whose light we'll never see? Each question nudges us closer to the edge of known physics, reminding us that the Big Bang wasn't just an event, it was the opening act of a story we're still learning to read. And as we peel back the layers of that ancient light, we might just find the missing pieces that reveal how everything, from the smallest atom to the grandest galaxy, owes its existence to the quantum tremors of a newborn cosmos. Imagine blowing up a balloon from the size of a grape to the size of Earth in less than a blink of an eye. That's the staggering speed of cosmic inflation, a theory proposing that the universe didn't just expand after the Big Bang. It exploded outward faster than light itself in the first trillionth of a second. This wasn't the steady growth we see today, but a runaway stretching of space, doubling in size over and over again, smoothing and flattening the cosmos like dough in a baker's hands. The idea emerged in the 1980s as physicists wrestled with three cosmic puzzles. First, the universe is unreasonably uniform. No matter where we look, the temperature of the cosmic microwave background varies by less than 1/100%. Without inflation, regions on opposite sides of the sky would never have had time to reach equilibrium, like two cups of coffee placed miles apart, somehow cooling to the exact same temperature. Second, space-time is eerily flat, balancing expansion and matter density with precision that defies chance. And third, we've never found magnetic monopoles, theoretical relics from the early universe that should be everywhere if not for an event like inflation diluting them to near nothingness. Inflation solved these riddles by suggesting the universe underwent a phase of hyper-fast expansion, driven by a mysterious field called the inflaton. As this field decayed, its energy flooded the cosmos with particles and radiation, the hot soup of the Big Bang we traditionally picture. But here's the twist: inflation didn't just smooth the universe, it also magnified quantum fluctuations, stretching microscopic ripples into the vast cosmic structures we see today. Those faint wrinkles in the CMB, they're the amplified fingerprints of quantum jitters, frozen in time when inflation ended, the theory's boldest implication. We might be living in just one bubble among countless others. If inflation can start once, why not over and over, spawning universes with different physical laws in an endless multiverse? Some regions could have stronger gravity or no light, or dimensions we can't fathom. It's a dizzying thought that our entire cosmos might be a speck in a frothing sea of realities, each with its own unique story. Critics argue inflation is hard to test after all. We can't rewind the universe, yet clues are mounting. The distribution of galaxies matches inflation's predictions, and tentative signs of primordial gravitational waves, ripples from inflation's violent expansion, have been hunted in the CMB's polarization. Future telescopes like the Light-Bird mission aim to catch these waves in action, potentially confirming inflation's wildest claims. What makes this theory so captivating isn't just its explanatory power, it's the way it reframes our origins. The Big Bang wasn't the true beginning. It was the aftermath of something far more dramatic. Inflation paints the early universe as a quantum roller coaster, where the tiniest fluctuations forged the largest structures, and the fabric of reality itself was stretched beyond imagination. And if the multiverse is real, it means our universe isn't just strange, it's one of infinite possibilities, each with its own laws, its own histories, and perhaps its own versions of us. Every second, trillions of nearly invisible particles streak through your body like cosmic ghosts, leaving no trace behind. These are neutrinos, nature's most elusive messengers, so lightweight and weakly interacting that they can pass through a light year of lead without slowing down. Born in the hearts of stars, the fury of supernova, and even the decay of atoms in your own home, neutrinos carry secrets from the most violent and mysterious corners of the universe. Yet for decades, they were little more than a theoretical footnote, first proposed in 1930 by Wolfgang Pauli to explain missing energy in radioactive decay. He famously bet his colleagues a case of champagne that no one would ever detect them, convinced their ghostly nature made them practically invisible. But science loves a challenge. In 1956, physicists Clyde Cowan and Frederick Wieniz proved Pauli wrong by catching neutrinos emitted from a nuclear reactor, earning a Nobel Prize and sending Pauli his promised champagne. The real surprise came decades later when researchers discovered that neutrinos aren't just hard to spot, they're shape shifters. As they travel, these particles oscillate between three distinct flavors: electron, muon, and tau neutrinos. This bizarre behavior proved they must have mass, however tiny, upending the Standard Model's prediction that they'd be massless. Suddenly, neutrinos weren't just cosmic curiosities. They were the first concrete evidence that our understanding of particle physics was incomplete. Nowhere are neutrinos more dramatic than in the death throes of massive stars. When a supernova explodes, 99% of its energy isn't emitted as light. It's carried away by a staggering neutrino blast. In 1987, detectors on Earth picked up 24 neutrinos from a supernova in the Large Magellanic Cloud, marking the first time we'd observed these particles from beyond our solar system. That handful of detections opened a new window into stellar collapse, revealing how neutrinos help drive the explosion itself, acting like a quantum pressure cooker that blows the star apart from within. Today, neutrino observatories buried deep underground, under Antarctic ice, or submerged in the Mediterranean Sea are hunting for even fainter whispers. Some search for relic neutrinos from the Big Bang, colder than the cosmic microwave background and far older. Others aim to catch neutrinos produced when cosmic rays strike Earth's atmosphere, or those emitted by the Sun's nuclear furnace. The most ambitious projects like Japan's Super Kamiok or the upcoming Deep Underground Neutrino Experiment could uncover even wilder possibilities like sterile neutrinos, a hypothetical fourth flavor that might interact only via gravity, potentially bridging quantum physics and dark matter. What makes these particles so thrilling isn't just what we've learned, it's how much remains hidden. Neutrinos could hold clues to why the universe favors matter over antimatter, a bias that allowed stars, planets, and us to exist. They might reveal new forces beyond the Standard Model, or even hint at extra dimensions. Every time we build a more sensitive detector, we're not just chasing ghosts, we're peeling back another layer of reality, one nearly massless particle at a time. And in their silence, neutrinos whisper a tantalizing truth. The universe is far stranger and far more connected than our eyes can see. Einstein predicted them a century ago, but even he doubted we'd ever detect them ripples in the fabric of spacetime itself, stretching and squeezing the universe as they pass. Then, on September 14, 2015, a billion-dollar gamble paid off. Twin detectors in Louisiana and Washington, part of the Laser Interferometer Gravitational Wave Observatory, or LIGO, caught the faintest whisper of a catastrophe that happened 1.3 billion years ago. Two black holes, each dozens of times heavier than the Sun, spinning toward each other at half the speed of light before colliding in a cataclysm so violent it momentarily outshone every star in the observable universe. The signal lasted just 1/5 of a second, warping LIGO 4 kilometer-long arms by less than 1,000th the width of a proton. But that blip, the first direct detection of gravitational waves, marked the dawn of an entirely new way to explore the cosmos. Before this, astronomy was like watching a silent movie. We could study light from radio waves to gamma rays, but gravitational waves let us hear the universe for the first time. Unlike light, which gets absorbed or scattered, these ripples pass unimpeded through dust, gas, even entire galaxies, carrying pristine information from events too dark or distant to see. Take neutron star collisions, city-sized stellar corpses so dense a teaspoon of their material weighs 1 billion tons. When two of these objects spiral together, they don't just emit gravitational waves, they forge gold, platinum, and other heavy elements in a kilonova explosion. In 2017, LIGO and its European counterpart, Virgo, detected such a collision alongside a burst of gamma rays and light, confirming in an instant that these cosmic crashes are the universe's ultimate gold factories. But the real promise lies in the unknown. Gravitational waves could reveal hidden populations of black holes, once too isolated or ancient to betray their presence any other way. Some theorists speculate they might even carry echoes from the Big Bang, a primordial hum from the universe's first trillionth of a second, when space-time itself was a seething quantum foam. Future observatories like the space-based LISA mission or next-gen ground detectors will tune into lower frequencies, potentially hearing the mergers of supermassive black holes or the faint tremors from cosmic strings, hypothetical defects in space-time left over from creation. What makes this revolution so exhilarating isn't just the discoveries we've made, it's how much we've yet to overhear. Every gravitational wave is a cosmic telegram sent across eons from events too extreme for our imaginations. And as our detectors grow more sensitive, we're not just listening to the universe's symphony, we're deciphering its deepest, darkest secrets, one ripple at a time. The universe is unimaginably vast, with hundreds of billions of galaxies, each containing billions of stars, so why does it feel so empty? This is the heart of the Fermi paradox, the puzzling contradiction between the high probability of extraterrestrial civilizations and the complete lack of evidence for their existence. Named after physicist Enrico Fermi, who famously asked, "Where is everybody?" this paradox has haunted scientists for decades. Given the age and size of the cosmos, intelligent life should have had ample time to arise, spread, and make its presence known. Yet our telescopes and radio dishes hear only silence. Could quantum physics hold the key to this cosmic mystery? One possibility lies in the nature of reality itself. Quantum mechanics suggests that particles can exist in superpositions, multiple states at once, until observed. Some theorists speculate that consciousness might play a role in collapsing these probabilities into a single outcome. If true, could it be that advanced civilizations have learned to manipulate or even transcend the fabric of reality, existing in states we can't perceive? Imagine a species that doesn't just explore space but engineers the very laws of physics, shifting into dimensions or quantum phases beyond our detection. What we interpret as an empty universe might be teeming with life that operates on entirely different physical principles. Then there's the idea of quantum communication. If extraterrestrials rely on entangled particles to send messages instantly across interstellar distances, our traditional searches for radio signals would miss them entirely. Entanglement doesn't involve electromagnetic waves. It's a silent, invisible link that bypasses the speed of light. We might be surrounded by a bustling galactic network, exchanging information in a way our technology isn't equipped to notice. It's like trying to hear a conversation in a crowded room while wearing earplugs. The signals are there, but we're tuned to the wrong frequency. Another quantum twist comes from the concept of simulation theory. If the universe is a vast computational construct, advanced civilizations might have figured out how to hack or exit the system, leaving behind the equivalent of a cosmic desktop we're still stuck in. Alternatively, they could be deliberately avoiding contact, treating our reality as a protected simulation, not to be interfered with a sort of quantum prime directive. But perhaps the most unsettling answer is that intelligent life is inherently self-limiting. Quantum physics shows us that observation changes the observed. What if the act of developing advanced technology inevitably leads to destruction, whether through environmental collapse, AI rebellion, or weaponized physics experiments? The universe could be littered with the remains of civilizations that reached a critical threshold only to vanish, their quantum footprints fading like echoes in the void. The Fermi paradox forces us to confront not just the silence of the cosmos, but the limits of our own understanding. Quantum theories offer tantalizing possibilities, but they also underscore how little we truly know about the nature of existence. Whether the answer lies in hidden dimensions, undetectable communication, or the fragility of intelligence itself, one thing is clear: the universe is far stranger than we've dared to imagine. And that silence out there, it might be the most profound message of all. Most of us think of crystals as beautiful, orderly structures, snowflakes with intricate patterns, or gemstones with repeating atomic lattices. But what if matter could form crystals not just in space, but in time? Enter time crystals, one of the most bizarre and groundbreaking discoveries in modern physics. Unlike ordinary crystals, which have atoms arranged in repeating spatial patterns, time crystals are structures that oscillate in a repeating cycle without any energy input, defying the usual rules of thermodynamics. Picture a clock that ticks forever without winding, or a perpetual motion machine that doesn't violate the laws of physics. That's the strange promise of these quantum curiosities. The story begins in 2012, when Nobel laureate Frank Wilczek first proposed the idea. He wondered, if crystals break the symmetry of space by repeating their structure, could there be a phase of matter that breaks time's symmetry, repeating its state periodically without energy loss? Initially, many physicists dismissed the concept as impossible. After all, perpetual motion is forbidden by the laws of thermodynamics. But Wilczek wasn't suggesting a machine that creates energy. He was describing a system that recycles it internally, like a quantum version of a frictionless pendulum swinging forever in its own rhythm. By 2016, two separate teams of researchers, one at Harvard, another at the University of Maryland, had brought time crystals to life in the lab. The Harvard team used a diamond riddled with nitrogen vacancies, while the Maryland group trapped a chain of ytterbium ions in an electromagnetic trap. Both setups exploited quantum quirks to create systems that flipped between states at fixed intervals, even when the external forces driving them weren't perfectly synchronized. It was as if the atoms were dancing to their own beat, ignoring the rhythm of the music. What makes time crystals so revolutionary isn't just their defiance of classical physics, it's what they reveal about quantum systems far from equilibrium. Most of physics deals with systems that settle into stable, low-energy states. Time crystals, by contrast, thrive in non-equilibrium conditions, offering a window into how quantum coherence can persist in dynamic environments. This could reshape fields from quantum computing to materials science. Imagine a quantum computer where information is stored not in fragile, static qubits, but in the robust, rhythmic oscillations of a time crystal, resistant to decoherence. Or consider sensors so precise they could detect infinitesimal changes in gravity or magnetic fields by tracking distortions in a time crystal's beat. The implications stretch even further. time crystals might help us probe the boundary between quantum and classical worlds, revealing how order emerges from chaos. Some theorists speculate they could model exotic phases of matter in neutron stars or even offer clues about the early universe's behavior. And then there's the tantalizing possibility of discrete time crystals, systems that repeat not just periodically but in quantum jumps, like a strobe light flickering in sync with the universe's hidden clockwork. Yet for all their potential, time crystals are still in their infancy. Researchers are just beginning to explore their properties, stability, and scalability. Each experiment peels back another layer, showing how these strange structures straddle the line between prediction and paradox. One thing's certain: time crystals aren't just a new phase of matter, they're a new way of thinking about time itself, proving once again that the quantum world refuses to play by the rules we thought we knew. Quantum teleportation sounds like something ripped straight from a Star Trek episode, beaming objects across space in an instant. But the reality, while no less astonishing, operates by rules far stranger than fiction. At its core, quantum teleportation doesn't move physical matter. It transfers the information of a quantum state from one particle to another, no matter how far apart they are. The magic lies in entanglement, that eerie connection where particles remain linked even when separated by light years. Here's how it works. Imagine Alice wants to teleport the quantum state of a photon to Bob. First, they share a pair of entangled particles, one for Alice, one for Bob. Alice then performs a joint measurement on her entangled particle and the photon she wants to teleport, collapsing both into a specific state. Instantly, Bob's entangled particle responds, mirroring the original photon state, as if the information has jumped across space. But don't pack your bags for a teleportation vacation just yet. The process has glaring limitations. For starters, the original photon state is destroyed during measurement, a consequence of the no cloning theorem, which forbids perfect copying of quantum information. You're not creating a duplicate, you're moving the quantum signature, leaving nothing behind. And while the entanglement link is instantaneous, Alice still needs to send Bob classical information via slow, old-fashioned light-speed communication to decode the teleported state. Without that extra step, Bob's particle is just a scrambled version of the original. So, no faster than light messaging here, relativity remains unbroken. The applications, though, are revolutionary. Quantum teleportation could form the backbone of a future quantum internet, where unhackable communication relies on entangled particles to transmit encryption keys. Experiments have already succeeded over distances exceeding 1,000 kilometers, using satellites to beam entangled photons between ground stations. In theory, this could scale to a global network, with quantum repeaters acting as signal boosters to prevent decoherence over long distances. But the wildest possibilities lie beyond mere communication. Teleportation might enable quantum computing's next leap, allowing qubits to be transferred between separate processors, stitching together modular quantum machines. Some theorists even speculate about teleporting complex molecular states, though teleporting an entire organism, as sci-fi dreams, would require coordinating an impossible number of entangled particles, not to mention the ethical quagmire of disassembling and reconstructing living beings. For now, quantum teleportation remains a laboratory marvel, a proof of principle that information can defy classical constraints. Yet every successful experiment nudges us closer to a world where distance loses its grip on data, and the lines between the possible and the fantastical blur just a little more. The future won't look like Star Trek, but in its own quantum way, it might be even more extraordinary. What if everything around you, the screen you're reading this on, the air you're breathing, even the thoughts in your mind, aren't real in the way you assume. This isn't the plot of a sci-fi movie, but a serious scientific hypothesis gaining traction among physicists and philosophers alike: the simulation theory. At its core lies a startling proposition that our universe might not be the base layer of reality, but an extraordinarily advanced simulation, running on some unfathomable computer built by a civilization far more technologically mature than our own. The idea isn't as far-fetched as it sounds. Modern quantum physics already paints a universe that behaves suspiciously like a pixelated video game when you zoom in closely enough. Take the Planck length, the smallest possible unit of space, beyond which the concept of distance loses meaning. It's as if reality has a built-in resolution limit, much like a digital image becoming grainy at high magnification. Then there's quantum indeterminacy, the way particles exist in probabilistic clouds until measured, almost like a computer rendering objects only when a player looks at them to save processing power. Even the infamous double-slit experiment, where particles act differently when observed, echoes the logic of optimization in virtual worlds, where unnecessary calculations are skipped until a user demands them. Philosopher Nick Bostrom formalized these musings in 2003 with his now famous trilemma. One of the following must be true, he argued. Either civilizations inevitably go extinct before developing simulation technology, they choose not to create ancestor simulations, or we're almost certainly living in one. Given the breakneck pace of our own computational progress, from room-sized computers to pocket-sized quantum processors in under a century, it's plausible that future societies could harness the energy of stars to power universe-sized simulations. If even a fraction of such civilizations run countless simulations of their ancestors, the statistical likelihood that we're in the original reality dwindles to near zero. But the simulation hypothesis isn't just about processing power. It reshapes how we interpret the deepest mysteries of physics. Dark matter and dark energy, which together make up 95% of the universe yet remain invisible, could be artifacts of the simulation's underlying code, background processes humming along outside the rendered world we perceive. Quantum entanglement's instantaneous connections might reflect the non-local operations of a master processor, bypassing in-world speed limits. Even glitches in the matrix, like déjà vu or the Mandela effect, could be explained as fleeting bugs in an otherwise flawless program. Critics counter that the theory is unfalsifiable, an elegant thought experiment with no way to test its claims, yet some scientists are actively seeking evidence. Seelers-Bean and colleagues have proposed that if our universe is a simulation, it might run on a lattice-like framework, leaving subtle imprints on high-energy cosmic rays. Others suggest that finding mathematical inconsistencies in fundamental constants, like the fine structure constant or the speed of light, could hint at programmed approximations rather than innate laws. Even the pursuit of a theory of everything takes on new urgency. Uncovering the universe's ultimate rules might reveal whether they resemble the elegant, compressed algorithms of optimized software. Beyond physics, the simulation hypothesis forces existential questions. If consciousness is just data in a program, does it still hold meaning? Could simulated beings ever break out of their reality? Or would that be like a video game character crawling out of the screen? Some thinkers argue that even if we're simulations, our experiences are no less real to us. Pain still hurts, joy still uplifts, and the search for truth remains valid. After all, as Descartes famously mused, "I think, therefore I am," doesn't require a flesh and blood body to hold weight. Whether the simulation theory is ultimately proven or debunked, its value lies in how it reframes our place in the cosmos. It invites us to question not just what reality is, but why it behaves the way it does and whether the answers might lie not in the stars, but in the circuitry of something far grander and more mysterious than we've dared to imagine. The search for life beyond Earth has always been a game of probabilities, scanning distant exoplanets for signs of water, oxygen, or other familiar markers of habitability. But what if we've been missing a crucial piece of the puzzle? Quantum mechanics, with its peculiar rules governing the smallest scales of reality, might hold the key to recognizing life in forms we've never imagined. From the way organisms harness light to the bizarre resilience of extremophiles in deadly environments, the quantum realm could be silently shaping the boundaries of life across the cosmos. Consider photosynthesis, a process so efficient that classical physics struggles to explain it. On Earth, plants and bacteria use quantum coherence to funnel solar energy with near-perfect precision, as if subatomic particles are conspiring to optimize every photon's journey. Now imagine an alien world orbiting a dim red dwarf star where sunlight is scarce. Life there might rely on even more sophisticated quantum tricks, perhaps exploiting entanglement to share energy across vast molecular networks, or tunneling through barriers to kickstart chemical reactions in freezing temperatures. If quantum biology gives Earth's organisms an edge, why wouldn't evolution elsewhere stumble upon similar or far stranger adaptations? Then there's the enigma of extremophiles, organisms thriving in conditions lethal to most life, boiling hydrothermal vents, acidic lakes, even the vacuum of space. Some microbes survive by repairing DNA damage at astonishing speeds, a feat that might involve quantum tunneling to relocate protons faster than classical chemistry allows. Others, like the radiation-resistant Deinococcus radiodurans, could be leveraging quantum coherence to protect their genetic code from cosmic rays. If life on Earth pushes quantum limits to endure harsh environments, what might evolve on a planet bathed in gamma rays or drowning in methane seas? The rules of quantum mechanics are universal, after all. The implications for exoplanet research are profound. Instead of just hunting for Earth-like atmospheres, we might need to scan for quantum biosignatures, subtle anomalies in a planet's chemistry or energy flow that defy classical explanation. Imagine detecting a gas imbalance that only makes sense if molecules are teleporting across membranes, or spotting infrared patterns hinting at energy transport too efficient for random collisions. Telescopes like the James Webb Space Telescope, paired with quantum sensors, could one day spot these fingerprints of quantum life. But the real mind-bender lies in the possibility of life forms built from entirely different quantum architectures. Silicon-based organisms might use superposition to stabilize their structures in scorching heat, while plasma-based beings in stellar atmospheres could rely on entangled states to communicate in the chaos of a star's magnetic field. The universe's creativity is boundless, and if quantum mechanics is any guide, life's potential is far wilder than we've dared to dream. This isn't just about finding aliens, it's about redefining what life even is. By embracing quantum biology, we're not just expanding the map of habitable worlds, we're rewriting the very definition of habitability. And somewhere in the silent dark between the stars, quantum life might already be doing the same. Space travel today is slow, expensive, and limited by the brute force physics of chemical rockets. But quantum technologies could rewrite every rule of the journey. Picture a spacecraft that doesn't burn fuel but rides the subtle tremors of spacetime itself, or a communication network linking Mars to Earth instantly, bypassing the agonizing lag of radio signals. These aren't just sci-fi dreams, they're the tantalizing possibilities at the intersection of quantum physics and space exploration, where the universe's weirdest rules become humanity's greatest tools. Take propulsion first. Traditional rockets rely on hurling mass backward to inch forward, shackled by the tyranny of Newton's third law. But quantum vacuum propulsion, a fringe yet fascinating idea, suggests we might one day push against the seething foam of virtual particles that quantum mechanics says constantly flicker in and out of existence in empty space. Imagine an engine that manipulates these fleeting quantum fluctuations, extracting momentum from the void itself. It sounds like magic, but experiments with Casimir cavities, devices that harness the pressure of virtual particles, hint that the quantum vacuum isn't entirely untouchable. Even more radical is the M-drive, a controversial concept claiming to produce thrust without propellant, though its physics remains hotly debated. While these ideas are far from practical today, they underscore a profound shift. The next giant leap in space travel might come not from bigger rockets, but from deeper quantum insights. Then there's navigation. Crossing the mind-bending distances of space demands pinpoint precision, yet GPS signals can't reach beyond Earth's orbit. Quantum sensors, leveraging the mind-bending sensitivity of entangled particles, could change that. Atomic interferometers, devices that measure tiny changes in gravity by tracking quantum waves in supercooled atoms, might map a starship's path using the gravitational ripples of planets and stars as cosmic signposts. Lockheed Martin and NASA are already testing quantum gyroscopes that could guide spacecraft without relying on external references, turning the ship itself into an unerring compass. And in the icy darkness of the outer solar system, where sunlight is a memory, quantum-enhanced cameras could detect faint infrared whispers from exoplanets or stealthy asteroids, revealing what conventional optics would miss. Communication is where quantum tech could shine brightest. Today, a message from Mars takes up to 20 minutes to reach Earth, a deadly lag for astronauts needing real-time guidance. Quantum entanglement offers a way out. By beaming entangled photons between planets, we could create a network where information is teleported faster than light, not by breaking relativity, but by leveraging the spooky link between particles. China's Misha satellite has already demonstrated quantum key distribution over 1,200 kilometers, and NASA Quantum Lab is prototyping interplanetary versions. The catch: the quantum link is fragile, and maintaining entanglement across millions of miles will require breakthroughs in quantum repeaters to amplify the signal without collapsing it. But if solved, a quantum internet could unite the solar system in a web of instant, unhackable communication. The coldest corners of space might hold the hottest quantum breakthroughs. Near absolute zero, where atoms nearly stop moving, quantum effects like superconductivity and superfluidity dominate. Future missions could deploy quantum telescopes with mirrors chilled to near 0 Kelvin, eliminating thermal noise to spot Earth like exoplanets directly. Europa's subsurface ocean or Enceladus's icy plumes might be probed by quantum sensors detecting subtle magnetic anomalies, hinting at hidden life. And in the ultimate cosmic irony, the void of space, often seen as a barrier, could become the perfect environment for quantum computers, where the cold and isolation prevent the decoherence that plagues Earth-bound machines. Imagine a spacecraft carrying a quantum processor to model asteroid compositions in real time or simulate alien atmospheres on the fly. Theoretical leaps loom even larger. Wormholes, those hypothetical shortcuts through space-time, might be stabilized by exotic quantum matter with negative energy, a substance hinted at in lab-scale Casimir experiments. Dark matter, which interacts so weakly with normal matter, could be mapped using quantum detectors sensitive to the faintest gravitational nudges. And some physicists speculate that quantum entanglement might someday be harnessed to teleport not just information, but energy itself across interstellar distances, redefining what it means to power a starship. The future of space exploration won't just be about going farther, it'll be about thinking smaller. Quantum technologies are teaching us to exploit the universe's hidden layers, turning the peculiar rules of the very tiny into the engines of the unimaginably vast. Whether it's a probe surfing quantum fluctuations or a colony on Mars linked by entangled particles, one thing's certain: the next era of cosmic discovery won't be powered by fire, but by the strange, shimmering laws of the quantum world. Quantum science isn't just reshaping our understanding of reality, it's forcing us to confront ethical dilemmas as profound as the technology itself. Consider quantum cryptography, where unbreakable encryption could safeguard personal data from hackers, but also shield criminal activity from law enforcement. The same quantum principles that promise secure voting systems and private medical records might also create black boxes for illegal transactions, leaving society grappling with an impossible question: how do we balance privacy and security when the tools to achieve both are fundamentally at odds? Then there's the specter of AI-driven quantum discovery. Machine learning algorithms trained on quantum simulations could unlock revolutionary materials or life-saving drugs. But what happens when these systems stumble upon knowledge too dangerous to share? Imagine an AI optimizing a chemical process that's equally effective for clean energy or a devastating bioweapon. Unlike nuclear research, where fissile materials are physically controlled, quantum insights exist as information, easily replicated and nearly impossible to contain. The same labs racing to build quantum computers might inadvertently arm bad actors with blueprints for catastrophe, all without a single physical trace. The ethical stakes skyrocket when quantum technologies intersect with human autonomy. Brain-computer interfaces leveraging quantum sensors could restore mobility to the paralyzed or enhance cognitive abilities, but who decides where therapy ends and augmentation begins? A world where neural implants exploit quantum coherence for hyper-fast processing might create a new class of quantum-augmented individuals, deepening societal divides. And what of consent? If quantum algorithms can predict human behavior with near-perfect accuracy, do we lose the right to unpredictability, the very essence of free will? Even environmental costs loom large. Quantum computers require cryogenic cooling near absolute zero, consuming energy at staggering rates. Pursuing quantum supremacy could exacerbate climate change unless breakthroughs in room temperature superconductors emerge. Meanwhile, quantum mining hypothetical techniques to extract rare minerals using quantum sensing might devastate ecosystems in the name of progress. The irony is palpable. Technologies meant to solve global challenges could accelerate them if deployed without foresight. Perhaps the most unsettling dilemma lies in quantum warfare. Nations investing in quantum radar and stealth-piercing sensors risk igniting an arms race where traditional defenses become obsolete. Hypothetical quantum spoofing could falsify satellite data, destabilizing global trust overnight. And while treaties regulate nuclear weapons, no framework exists for quantum tools that blur the line between offense and espionage. The very science meant to connect us might push humanity closer to fracture. These aren't distant concerns, they're unfolding now, as ethicists scramble to draft guidelines for a field outpacing its own implications. The lesson is clear: quantum physics doesn't just challenge our knowledge of the universe, it demands we redefine our moral compass. The power to manipulate reality's fabric comes with a responsibility equally vast, and how we navigate these crossroads will shape not just science, but the soul of civilization itself. Quantum physics has become a magnet for wild misconceptions, partly because its bizarre concepts are so often stripped of nuance in pop culture. One of the most persistent myths is that quantum mechanics proves reality is entirely subjective. that particles behave differently simply because we choose to observe them. While it's true that measurement affects quantum systems, this isn't about human consciousness magically shaping outcomes. In labs, detectors and instruments trigger the same wave function collapse without any human present. The real shocker isn't mind over matter. It's that interaction itself defines reality, whether that interaction comes from a person, a machine, or even another particle. Then there's the oversimplification that quantum entanglement allows for instant communication across the universe. Sci-fi loves this idea, but here's the catch. While entangled particles do mirror each other's states faster than light, you can't control what those states will be. It's like having two synchronized coins. Flipping one instantly determines the other's outcome, but you can't force them to land heads or tails on demand. Without the ability to encode information in those outcomes, entanglement becomes cosmic sync without a message. This limitation preserves Einstein's speed of light barrier, keeping quantum weirdness from breaking causality. Another common exaggeration is that quantum computers will soon replace classical ones for everything. The truth is far more specialized. Quantum machines excel at specific tasks, like factoring large numbers or simulating molecules, but they're terrible at basic operations like email or spreadsheets. Think of them as specialized power tools rather than universal replacements. Even when mature, they'll likely work alongside classical systems, each handling what they do best. And despite the hype, we're still decades away from quantum laptops. Current qubits require near absolute zero temperatures and error rates so high they'd crash your phone in seconds. Perhaps the most dangerous misconception is that quantum physics validates pseudoscientific claims. From healing crystals to quantum manifesting, opportunists hijack the field's mystique to lend credibility to nonsense. Real quantum effects are subtle, fragile, and rigorously tested, not magical forces you can harness with positive thinking. The Heisenberg uncertainty principle doesn't mean your thoughts alter reality. It means particles don't have definite properties until measured. Schrödinger's cat was a thought experiment mocking quantum absurdity, not a recipe for parallel universes where you're suddenly rich. What quantum science can do is equally astonishing, if less flashy. It explains why the sun shines through nuclear fusion, enables MRI machines to peer inside our bodies, and makes modern electronics possible. It's reshaping encryption, materials science, and even our understanding of life itself through quantum biology. The truth about quantum physics isn't that it's less amazing than the myth. It's that its real wonders are stranger, richer, and far more transformative when you ditch the hype and embrace the nuance. The next time someone claims quantum mechanics proves anything is possible, remember, the universe's deepest truths aren't magic tricks. They're invitations to explore, question, and marvel at the genuine mysteries still waiting to be solved. What does the future of quantum physics look like through the eyes of those shaping it? Dr. Michelle Simmons, a pioneer in quantum computing at the University of New South Wales, describes the next decade as a race to build error-corrected quantum machines, not just with dozens of qubits but thousands. Right now, we're like the Wright brothers learning to keep our quantum planes airborne for a few seconds, she explains. But imagine when we hit the equivalent of jet engines. We'll simulate entire molecules atom by atom, designing materials with properties that defy classical intuition. Think room temperature superconductors or solar panels with near-perfect efficiency. Across the Atlantic, Dr. Charles Marcus at the Niels Bohr Institute paints an even wilder picture. His teams work on topological qubits. Particles protected by their geometric structure could solve quantum computing's Achilles heel, decoherence. It's like building a sandcastle that doesn't crumble when the tide comes in, he says. Within 10 years, Marcus predicts these robust qubits will enable the first practical quantum internet nodes, linking cities through entanglement-based networks where data travels securely at the speed of thought. But not all breakthroughs will happen in labs. Dr. Shohini Ghose, a quantum physicist and advocate for equity in STEM, emphasizes the societal shifts ahead. The quantum revolution isn't just about hardware, it's about who gets to wield it, she notes. Her research highlights how quantum sensors could democratize healthcare, with portable MRI machines detecting tumors earlier in remote villages, or quantum algorithms optimizing renewable energy grids for underserved communities. The real milestone, when quantum tech becomes invisible, woven into everyday tools so seamlessly that a farmer in Kenya benefits as much as a Wall Street trader. Then there's the enigmatic Dr. Brian Greene, whose work straddles quantum mechanics and string theory. He envisions experiments that could blur the line between quantum and cosmic scales. We're on the verge of testing whether black holes obey quantum rules, he reveals. Projects like the Event Horizon Telescope might soon spot quantum signatures in the swirling plasma around Sagittarius A, our galaxy's supermassive black hole. If spacetime itself has a quantum structure, these observations could be our first glimpse of gravity's quantum code. The most provocative forecast comes from Dr. Michio Kaku, who believes quantum biology will upend medicine. We'll discover enzymes using quantum tunneling to cure diseases, he asserts. His team models how quantum vibrations in proteins might explain anesthesia's mechanism, a mystery since the 1800s. Cancer, aging, even consciousness, these could all have quantum roots we're just beginning to decipher. Yet amid the optimism, caution lingers. Dr. Stephanie Weiner at Delft University warns of a quantum divide. Nations without quantum infrastructure will become data colonies, she says. Her solution, open-source quantum education programs training a global workforce. The next Einstein might be coding in Nairobi or Lima if we give them the tools. What unites these visionaries isn't just excitement, it's urgency, as Dr. Simmons puts it. This isn't incremental science. We're rewriting the rules of reality, and the ripple effects will touch every life on Earth. Whether it's unbreakable encryption or starship navigation, the quantum future isn't a distant dream, it's being built today, one qubit at a time. As we stand on the brink of a quantum revolution, the mysteries of the cosmos are more tantalizing than ever. Think about this. Just over a century ago, physicists believed the universe operated like a predictable clockwork machine. Today, we know it's more like a vast, interconnected quantum network where particles wink in and out of existence, entangled across galaxies, and space-time itself bends under the weight of invisible matter. The scale of this transformation isn't just technical, it's philosophical. Every experiment, from the double-slit to gravitational wave detectors, peels back another layer of reality, revealing a cosmos far stranger and more wondrous than our ancestors could have dreamed. Consider how far we've come. Max Planck's quantum hypothesis began as a desperate fix for a physics problem. Now it underpins everything from smartphones to solar panels. Einstein dismissed quantum entanglement as spooky action at a distance. Yet today, we're building global networks that rely on it for unbreakable encryption. Black holes, once thought to be cosmic vacuums, are now laboratories for testing quantum gravity, their secrets slowly unraveling through Hawking radiation and holographic principles. And dark matter, which makes up 27% of the universe, remains an enigma, taunting us with clues we're only beginning to decipher. But the quantum leap isn't just about rewriting textbooks, it's about redefining what's possible. Imagine a future where quantum computers design life-saving drugs in minutes, where entanglement-based communication links colonies on Mars to Earth instantaneously, where we finally understand the birth of the universe itself. This isn't science fiction, it's the trajectory we're already on. The breakthroughs of the next decade could eclipse everything we've achieved in the past century, turning today's wildest theories into tomorrow's everyday tools. Yet for all our progress, the universe guards its deepest secrets fiercely. Why does quantum mechanics work the way it does? What or who might be out there in the cosmic dark, shaped by the same quantum rules that birthed us? The more we learn, the more we realize how much we don't know, and that's the true beauty of this journey. The unanswered questions are just as thrilling as the answers. So stay curious, keep questioning, because the next cosmic revelation might not come from a lab or a telescope, but from someone watching the stars and wondering just like you. The quantum revolution isn't a destination, it's an endless frontier, and we've only just begun to explore. Who knows what's next? One thing's certain, the universe will keep surprising us, and that's the greatest adventure.